All right, class, welcome to the topics for Module 8. So I'm going to do some examples and show you how to do goodness of fit tests and one-way ANOVA in StatCrunch so that you can continue to avoid having to use these formulas and you can just do it all using the software. The first thing is, given some sort of probability distribution, finding an expected frequency distribution. Essentially, all we're doing is we're taking this. So we have in this situation we're describing some probability distribution. The value can be 1, 2, 3, or 4, and the associated probabilities are 0.16, 0.37, 0.61, and 0.31. If you can picture in your mind a four-sided die that's weighted in an unfair way, that's what this is representing. So we want to roll this die 722 times, and I want to ask, what do I expect to get out of this? Like, how many times would I expect 1 to come up? How many times would I expect 2 to come up, and so forth? Simply put, I would expect 16% of my 722 rolls to be a 1, right? So it's just 722 times a 0.16. That's all we have to do to get the answer here. But we can do this without actually doing any calculation on our own. I'm going to show you how you can create an expected frequency count from StatCrunch. And this is especially helpful if you had a vast probability distribution. So let's copy it in StatCrunch. All right, so I've got my values and my probabilities. So here's the way we can, in order for us to get the expected frequency count, we have to do a little bit of a cheaty thing. Here's what you can do, all right? So what we want to do is, let's just call var3, this is, I'll call it n. And what I'm going to do is put 722 in column 1, or in row 1, and I'll put some zeros. So this is just a way for me to say that I want to do 722 trials. This is a little bit of a workaround, but I'll show you what this gets for us. So I'm going to go to the stat menu and go to a goodness of fit test, chi-square test. What is observed is my n. I'm going to pretend that I got 722 times, but that doesn't even matter. All I'm getting is the expected frequency count. That's what I want. The expected are the probabilities in the pi. This is probability subscript I, pi. Those are what's expected, the expected relative frequencies. Click compute and you'll see what you get. So isn't that nice? So forget about this observed, that doesn't matter. What we have is these expected values for 1, 2, 3, and 4. So we can copy those right in. Now we're going to do a goodness of fit test, a chi-square test for this. We observed the values 0, 1, 2, 3, and 4 these many times. This is what we expected. And so for a binomial random variable, we would have expected to see these values. So we want to check, is a binomial distribution a good fit for this random phenomenon, whatever it is. I know we haven't talked about what binomial variables are, but we don't really need to know what a binomial variable is. So suffice it to say, if x was a binomial, we would have, after observing this phenomenon this many times, we would have gotten 1.6 zeros, 25.2 ones, 151 twos, 402.6 threes, 402.6 fours on average, or in expectation, right? You know, we're never going to get exactly 1 point. If this is we're rolling the die, whatever it is, you're never going to get the number 0 to come up 1.6 times. That doesn't make any sense. With expected frequencies, that's an on average. It's like a long-term average, so it's a theoretical average for this, right? That's okay. I mean, for calculating whether this follows the model, it's okay for us to have little decimal places in there. So here's how we do it. We're going to click this little button, open this in StatCrunch. All right. So we've got of our observed and expected. So under the stat menu, go down to goodness of fit, chi-square test. Our observed is observed, and our expected is expected. Well labeled. And we just click compute. So what do we have here? We've got, so for what we've observed versus what we would expected, we got a chi-square value of 14.232. This is, the chi-square is the test statistic that we calculate for this type of a problem. So if the chi-square, loosely speaking, what we observed is vastly different from what we expected, the chi-square test statistic will be bigger and bigger and bigger. If what we observed is very close to what we expected, the chi-square value was going to be close to 0. So if a chi-square value is really, really big, we're going to get a very small p-value, and we would reject the null hypothesis that this is a good fit for our model. Like this distribution matches what we got in practice. So anyway, let's copy the chi-square value in here and let's walk through the rest of the problem. How many degrees of freedom? It tells it to us right here. There's 4 degrees of freedom. df is degrees of freedom, 4 degrees of freedom. It's, in this case, it's one less than the number of we call them treatments or levels for this single factor, but don't worry too much about that. It's given to you right here in the output table. df is degrees of freedom, 4 degrees of freedom. The critical value for chi-square. To answer that, let's go up to the stat menu, calculators, pull up a chi-square calculator. For a chi-square calculator with degrees of freedom of 4, we want to find what's the critical value that's going to leave only 0.05 in the tail. 0.05, put it down here, compute. Remember, we're doing this inverse. And here's, oh, I want the upper tail, not the lower tail. So let's do that again, 0.05, click compute. Here we go. So the critical value is 9.48. 7, so it's 9.488. 9.488. So if our test statistic is in that red region, right, if it's bigger than 9.488, then we would reject the null hypothesis that the random variable is binomial. We would reject this expected distribution. We would say, nope, we are not matching it. This is probably not what our variable is doing. So should the null hypothesis be rejected? Yes, because chi-square is greater than the critical value. Okay, a manufacturer of colored candies states that 13% are brown, 14% are yellow, 13% red, 24% are blue, 20% are orange, and 16% are green. I wonder what those colored candies could be. A student randomly selects a bag of colored candies. He counted the number of candies of each color and obtained the results shown in this table. Let's open the table and let's throw that into StatCrunch because we're going to need it in StatCrunch. So we have proportions versus what we actually observed. So when we're doing a chi-square test, we can either put in expected frequencies or expected relative frequencies, expected proportions. So the null hypothesis would be that the manufacturer's claims are accurate. The alternative is that they're not accurate, okay? So the status quo, the less interesting, is the null. The distribution of colors is the same as stated by the manufacturer is the null, and the alternative is that it's not the same, okay? So what is the expected count? Let's do under stat menu, we can do our goodness of fit test, a chi-square test. We're going to say what we observed and the frequency. what was expected in the claimed proportion, it's going to bring that all the way up to expected frequencies, and that's what we're going to have here. We're going to copy this. We have, what, 2 decimal places, so this is perfect. 51.87. We have 55.86 for the second color. We have 51.87, 95.76, 79.8, and finally 63.84. All right, great. Those are expected counts, the chi-square test statistic. It's given right there in our output. It's 16.141. P-value is also given, and we have 3 decimal places, but that would round it up to 0.007. 0.007. Tiny p-value means we reject the null hypothesis. Reject the null hypothesis. Let's see. There is sufficient evidence that the distribution of colors is not the same as the manufacturer. Oh boy. Something fishy going on at the colored candy factory. Okay, now we're going to move on to ANOVA, which stands for Analysis of Variance. An analysis of variance table is always going to look pretty much like this, and calculating the values can be done using a calculator. I wish that we could do this without actually pushing any buttons, but it's pretty easy to do. So what we have is 3 rows: the treatment, the error, and the total. Okay, so in all of these cases, the total row is going to be the total of the 2 numbers above it. Very simple, it's just addition. Now, to find the means, so we have the sum of squares for the treatment, the degrees of freedom for the treatment, then the mean squares. This is to say, what's the sum of the square per degree of freedom? So to find this number, we divide the sum of the squares by the degrees of freedom. The F statistic is the mean square for treatment divided by mean square for error. 0.680. Alrighty. That's how you fill out an ANOVA table. Now, ANOVA is useful for a number of things, but one thing is if the comparing the means for more than 2 populations, more than 2 samples, so 3 or more samples. So let's see an example. At a community college, a mathematics department has been experimenting with 4 different delivery mechanisms for content in their intermediate algebra courses. One method is the traditional lecture, method 1. The second is a hybrid format in which half the class time is online and the other is face-to-face, method 2. The third is online. The fourth is an emporium model from which students obtain their lectures and do their work in a lab with an instructor available for assistance. Method 4. Okay. So there's 4 methods. That's all. To assess the effectiveness of the 4 methods, students in each approach are given a final exam with the results shown in the accompanying table. Ooh, let's look at the table. Numbers. Oh, look at all those numbers. That's too much to look at outside of StatCrunch. Let's put it in StatCrunch. I'm being facetious, but really, we're going to do all this stuff in StatCrunch, so that should be the immediate thing to do with all of this data. Bring it in StatCrunch. Okay, do the data suggest that any method has a different mean score from the others? Well, the null hypothesis in situations like this would be that all the means are equal to each other. The alternative is that at least one of them is different. So that's the only way we phrase the null and the alternative in this case. So the null is that all the means are equal. So this is mu1, this is mu, the population mean for approach 1, equals mu2, equals mu3, equals mu4. I don't know what they are, but they're all equal. That's the null hypothesis. It's just claiming they're equal. It doesn't claim they are equal to any particular number, just that they're all equal. The alternative is that at least one of them is different. They could all be different from each other, but at least one of them is different. Okay, that's the null and the alternative. Requirements for an ANOVA procedure. We need to have case samples independent of each other. That's necessary. So we have, in this case, we have 4 samples. We need to have 4 simple random samples, and each one is coming from one of the 4 populations. That's another requirement. The populations, they don't have to be normally distributed with the same mean, but they should be normally distributed or close to normally distributed with the same variance at least. And that's the 3 requirements. They should not be from the same population. So we're given an ANOVA table. Cool. Maybe we don't have to run it ourselves, but you know what I'm going to do? I'm going to create my own ANOVA table, because how do I know that that's right? I'm going to go into StatCrunch. I'm going to go to Stat. I'm going to go to ANOVA, a one-way ANOVA. And I'm going to select all 4 of these and click Compute and make my own ANOVA table, because I can. So let's just compare. We've got 3, 702, 67. Yeah, okay, fine. The numbers are the same, but just wanted to double check it. That's how you create an ANOVA table from data. So, but they're giving it to us here, so that's nice. So we're basing it on the p-value. This is a p-value of 0.223. Should the null hypothesis be rejected? Well, that's a pretty high p-value. We would normally only reject, and here we're using a 0.05 significance level. This 0.223, that's not greater than that's greater than the significance level. That means we do not reject. Do not reject. There is insufficient evidence to support H1, the alternative hypothesis. So let's see, side-by-side box plots. That's what they look like. I don't trust that. I'm going to make my own box plots. All right, let's go over to StatCrunch and just practice making side-by-side box plots again. Box plots, I'm going to select all 4 of them, and I'm going to do horizontal box plots and color scheme, basic 7 colors. I don't need to do anything else. Just click Compute. Okay. Yeah, I guess that's right. That matches pretty much. Although it looks like I think that in their box plots they're putting the mean as that line instead of the median. Let's just check. I'm gonna put the mean in as green lines. No, I feel like they messed up on that top one. I don't know. I feel like that's off. Yeah. This is not the same. But I'm not gonna get too obsessed over it. They're telling me that those are the box plots, so I'll just take it. Okay. So what do we want to ask? Shown side by side, do the box plots support the result obtained? Like, from these box plots, is it reasonable to assume that all these populations have the same mean? Yeah, I mean, pretty much. They're like the middle that middle 50%. That's overlapping on all of them. There's a common overlap, even in mine. So I would say, yeah, it supports. It doesn't show that they have significantly different means. So I would say, yeah, that's fine. Interpret the p-value. Since the p-value is not less than alpha, since it's greater than or equal to alpha, that there is insufficient evidence that any one method is more or less effective than the others. Yeah, that's how you interpret a p-value in this case. Verify the residuals are normally distributed. Okay, so let's look at the residual plot. Make a normal probability plot of residuals. So let's go back here. Let's go to Stat. Let's go to actually on our ANOVA, our one-way ANOVA. I want to graph a what's called a QQ plot of the residuals. A QQ plot of residuals is what we're asked for here. I'm going to click compute, and oh, I didn't select my variables. Variables. A QQ plot of residuals. It's going to be the second screen here. This is I'm not getting those little curvy bound things that it has here, but what I've got here is residuals versus normal quantiles. I'd like to flip this around, and I don't know if I am able to do that. This is a little bit frustrating. Okay, you can see that on these examples we've got residual as the x-axis and z-score on the y-axis. It looks this plot looks like it looks a bit like A and B, but I'm gonna look at B first. The problem is that my axes are flipped, so I'm gonna have to use my imagination to flip this stuff around. Unfortunately, that's kind of hard to do. I've got so we're trying to look at this pattern to see those. So we have this line that goes down, this diagonal line, and we want to compare this. So this looks pretty good, although that point is not too close to the line. I'm going to go back to the other one. So you have to imagine, you flip it over and see if it would match. No, this isn't the right shape. I'm going with this with choice B. That's closer. I know you had to do a mirror image to see it, but it's there. Anyway, what does a QQ plot mean? If these dots are along the diagonal, then that pretty much tells us that, yeah, the populations are pretty much normally distributed. The plot is approximately linear. I mean, that's fine. We don't have to be too picky. It is approximately linear, so I'm going to say, yeah, we have normality in our samples. A highway safety institution conducts experiments in which cars are crashed into a fixed barrier at 40 miles per hour. In the institute's 40 mile per hour offset test, 40% of the total width of each vehicle strikes a barrier on the driver's side. The barrier's deformable face is made of aluminum honeycomb, which makes the forces in the test similar to those involved in a frontal offset crash between two vehicles of the same weight, each going just less than 40 miles per hour. You are in the market to buy a family car and want to know if the mean head injury resulting from the offset crash is the same for large family cars, passenger vans, and mid-size utility vehicles. Okay, the data in the accompanying table were collected. So let's open the table. Let's bring it into StatCrunch. And then we're going to do some ANOVA. Right, what we're interested in is whether the mean value for the three samples is the same, right? If let me say it a different way. We want to see if this data supports the hypothesis that, well, all three of these types of cars have the same mean collision value, whatever it is, or whether one of them is different. And that's what we're looking for. The null hypothesis that the mean for cars equals the mean for vans equals the mean for SUVs, and the alternative is that at least one of the means is different. So if normal probability plot indicate that the sample points come from normal populations, are the requirements to use ANOVA satisfied? Yeah. Well, as long as we've got random samples and it says that this institute study, yeah, I mean, I think this is fine. But let's just check. Let's go back to StatCrunch and let's just do a little stat. Let's calculate summary stats for all of this data. Here's what I want to compare. I'm going to compare their standard deviations. Okay, I'm going to compare them and let's see. Standard deviations 197, 188, 128. We want to ask, is there sufficient kind of evidence here to suggest that one of the populations has a vastly different variance? Well, I don't know. I think that we can probably, I mean, you can see that the mid-sized utility vehicles have a smaller standard deviation than large family cars. But I think that that's fine. Certainly look at choice C. The largest sample standard deviation is more than twice the smallest. No, that's not true. The samples are independent. The populations, yeah. Let's see. Let's see if they're normally distributed. We can do that by doing a normality test on our data. Let's just throw all this stuff in and just run a normality test and see what we get. Normality test it's a very easy way to test if your data is is normally distributed. So you've got your sample and the hypothesis test is null hypothesis. The data is normally distributed. Alternative, it's not. So if your p-value is small, you would reject the null hypothesis. All of these p-values are bigger than, say, 0.05. So there's no reason to say any one of these is not normal. So we're going to say they're all normal. So yeah, everything's there. All the requirements are there for doing a ANOVA. So let's do the ANOVA. Let's do stat ANOVA, a one-way ANOVA. And let's get our data, click compute, and we have our ANOVA table, which has an F statistic in it to 3 decimal places, 0.391. All right. And the p-value here is 0.68. I'm taking what, 3 decimal places? Oh, 4, 1, 8. The p-value is big. That's very big. I don't want to reject the null hypothesis. So there is insufficient evidence to reject the null hypothesis. Thus, we what? Cannot conclude that the means are different. Certainly not at an alpha level of 0.01. 0.68 is a very big p-value. Box plot for the 3 vehicles. Okay, now let's do our box plot. Let's close this stuff. Or let's move it to the side. Stat, or no, it's graph. Graph box plots. Let's do side-by-side box plots and make them horizontal. And click compute. We've got boop-a-doop-a-doo. All right. We've got large family cars, passenger vans, and SUVs. So we should have SUV, van, cars. And it looks like it matches this. I think so. Yeah, for sure. Great. Well, anyway, that's how we do ANOVA in StatCrunch. I hope you do well on the assignment. And let me know if there's anything you need. All right. Bye.